Okay, we will start the second round. The reporter is XUQ Delta, and the opponent is NXWO2, and our reviewer is Xiaoya, and the stage is the preparation of the reporters. Three teams write down the representative name. in the presentation of the reporter.
Thank you. So, good morning everyone. I'm a reporter from Team 10CompX Entrepreneur, and I'm reporting problem number 4, ball sound. So let's look at the problem statement. The problem statement asks us that when two hard steel balls or similar are brought into contact with each other, an unusual chirping sound may be heard. Investigate and explain the nature of the sound. So during this process, we will try to investigate what exactly is the nature of the sound. Why would we hear such a chirping sound? And what will this sound, how will this sound be produced, and what will affect this chirping? So first of all, what is chirping? So we have to define what is chirping. So we believe that chirping is a sound with continuous increasing or decreasing frequency. Well, let's give a short example of what exactly is chirping. Okay, so now we know that with a sound with continuous increasing or decreasing frequency, we will hear, experience, and consider it as a chirping sound. Now let's look at what will we hear when we have two steel balls together. So we believe that there are two ways to bring two steel balls together. Well, one way is using the Newton's cradle, which when we contact it moves on to another side. And another way is using my hand. When I bring the two balls gently together, these two balls will stay together and will have different sounds. So let's first listen to the sound of the Newton's cradle. Okay, a single collision. And what about the other observation? Okay, we have clearly a difference. The difference is we have here a slightly, we experience a slightly difference in hearing. Well, we're not exactly sure what exactly is the frequency changing, the sound changing, or what is changing. So we want to investigate, is this exactly the chirping sound we observe, and does it fit the definition of frequency changing? So let's look at the sound wave. Well, the sound wave of the first graph is like this, the second graph is like this. So there's a really clear difference, and we will now move on to investigate. Well, we have defined the chirping sound as a continuous changing of frequency. Well, if we speak of frequency, the first thing we will come to is Fourier transform. Well, to do Fourier transform is simply expanding signals in terms of sinusoidal waves. So it simply expands the wave into different adding of sinusoidal waves. So it tells us whether it's added by different sine waves. So it is an example of its mathematical transform. If we have the f of x and we do sinusoidal transform to this, do Fourier transform to such a result, then we'll get such a function like this. So this is a short example. This is the wave pattern. If we do the Fourier transform to this, it will give us a clear peek of what exactly add up to this wave. Now, this is the Fourier transform of our chirping sound. This is the first graph. We said that the sound pressure graph. Now, if we do Fourier transform to this, well, the first problem is the frequency changing? Well, we don't know. This is simply a response graph of whether the frequency and in this sound is. So we move on to discuss well, the disadvantage of Fourier transform. We can't get the time-dependent results. We don't know that during the time scale will it affect will the frequency change or not. And we also cannot get representing for discontinuities or sharp corners. So we have to move on for another method, and we use the short-time Fourier transform. The short-time Fourier transform is simply cutting it into different time slices and produce Fourier transform. So if this is the graph, cut it into window length, and this will be the Fourier transform we do to our experiment. So this is the software we use, simply origin, and we analyze is there such sort of frequency changing. So this is the graph of the first collision, the one of the Newton's cradle. As you can see, there is no significant change in frequency inside this graph. However, for the second graph, the graph of the chirping sound brought together by hand, we see a clear increase of frequency right here. And well, there is another response here and a response here. So then we'll move on to discuss what exactly is the mechanism behind this phenomenon. So we move on to the investigation of mechanism. The mechanism of this, well, we come back to the sound pressure graph. The sound pressure graph, we see a lot of peaks here. Well, a single sound wave, a single collision, we believe that it will not produce so many peaks. So we believe that the hypothesis is maybe there are many collisions during this process. So to validate it, we have to use a certain device. Well, we believe that the electrical current is a really nice device to validate if it's touching each other or not. So this is the device we use. Well, we simply connect the ball to a motor sensor. When it's apart, it will get high readings. And when it gets together, since it's short-circuited, it will get a low reading. So by doing this, we will get that whether the ball are in contact or not. So to move on, we also record the sound simultaneously to make sure that the peak is at the same place. So this is the experimental device. And here is the result. Well, as you can see, the Milton collision of this graph is shown. This is the one when we bring together by the magnet we use. We replace our hand with a magnet to use the force that acting on each other constant throughout this collision. And in this graph, you can see that for each collision, you can see a clear peak in the sound pressure, which has validated there is actually multi-collision throughout this process of producing this chirping sound. And as for the one of the Newton's cradle, as you can see, there is just simply a single down in the electrical potential, which means that there is just single collision producing a single sound. Well, then we're curious about which exactly produced the well, we now validate that a series collisions when the chirping happens. Now, what exactly is this part? What contributes to this part of the increase of the frequency? So we go back to look at it again. So looking at this graph, you can see that the time gap between collisions are decreasing clearly. And so we believe that maybe will this time gap affect the resulting pattern we see. So we simply take the time gap and inverse it to make it the frequency, the equivalent frequency. And we take this graph to correspond to the short time Fourier transform graph. You can see that the blue line is the white line we see back in the short time Fourier transform. And we can see that this two graphs corresponds really well, which means we believe that the result of increasing frequency inside the chirping sound is contributed by the multi-collision and the decreasing of frequency throughout this process. So it sounds like increasing frequency, which we at last recognize a chirping sound. Now we move on to the theory. What exactly affects the time gap? So for the time gap part, we will make two small assumptions. Well, first, during the contact area, the displacement is really small. So we make a simplification that the magnetic force is nearly a constant. And then the impact is an inelastic collision with a coefficient of restitution of E. Well, this is simply to make us get the relationship between two different velocity impact and when it leave it. So if I have a ball contacting, and the impact velocity is v0, the leaving velocity will be E times v0, and then we assume that since it is a constant for acting, the resulting velocity coming back will still be v0. And under the assumptions of the constant force, we will get the constant acceleration. So this will be an acceleration. And the changing of velocity will give us the time gap. The time gap between two collisions will become delta V over A. So the delta V over A will give us this relationship. And we're mainly investigating about how the mass and the force affect this phenomenon. Okay, so this will be the experiment part. We investigate on various parameters. First is the mass of the ball, and the force between the ball. We're simply adding magnets to the ball we are impacting. Okay, so this is a result of the magnetic field because we change the magnets on the ball, and this actually experimental data we record or we collected. And as you can see, when the force is bigger, the time gap is actually bigger, which corresponds to our theory well. And well, what about the mass? As you can see, when the mass is bigger, also the time gap is bigger too. Oh, sorry, I explained the inverse relationship here. It should be like in another way. I'm sorry. And so now we move on to the simulation. We want to try to simulate such a process. Can we actually make it by our hand? Can we actually make such a process by simply using sinusoidal wave? So using sinusoidal wave, well, here we are trying to claiming that actually the time gap will affect our hearing. The time gap will be the main phenomena affect our hearing. Not just the frequency of the sound itself, not just the period of the sound itself, but also the time gap will affect our hearing. So let's first listen to 4,000 hertz sound. Okay, so we can hear it's a 4,000 hertz constantly. Now what would happen if we use still 4,000 hertz, but adding 0.001 second of time gap to this sound wave? What will happen? So this is the way we use. We first connect a series of 4,000 hertz wave and the one with time gap. So let's play it. So as you can see clearly, as you can hear clearly, the time gap will actually affect our hearing. This is the same 4,000 hertz sound, the sinusoidal 4,000 hertz sound, but the time gap will actually affect our hearing and the resulting SDFT graph. Now, here we want to simulate the impact sound. So the impact sound is like this, with decreasing time gap. So here we take a 4,000 hertz sound and simply adding decreasing time gap to it. So let us hear what will happen. This one is from this simulation. This is not the sound recorded. So as you can see, it is qualitatively really similar to the one we recorded of the chirping one. And next one, if we take triple wave, this is just single wave here, and we take triple wave here, what will happen? And now we have the comparison to the original sound. This one is the original sound, and this one is the sound simulated. So as you can see, this is in clear similarity. So we believe that we have successfully explained what exactly the nature of the sound have formed. So now we move on to the conclusions. We have validated experimentally that continuous collisions will happen when the chirping sound is recognized. And the decreasing time gap between collisions will contribute to increasing sound frequency, which affects our hearing and the STFT graph. And the time gap which affects our hearing will be related to the mass of the ball and the force between the balls. And that's all for our report. Thank you.
Opponent questioned the reporter, and the reporter answered the question. Great report, and I asked a few questions. So why can you explain why do you consider magnet as a force?
Okay. The magnetic force is actually related to the distance.
Yes. Related to R squared.
Yeah, I know. We are assuming that the distance that is moving is really small to make such simplification.
So do you think the size of the ball will affect?
The size of the ball without affecting the mass?
Yes.
We believe no.
Okay. Why do you think is steel ball necessary?
Well, we believe that the steel ball has a certain property. It's not the steel important, but because we have to form the sound is the origin of vibrating. So if there is plastic deformation, like when I use a plastic ball and I push it, and then it forms, and it will be no sound.
Okay. So since in your experiment you have mentioned about equivalent frequency and actually the frequency of the sound. So how do you actually define the frequency in your experiment?
Okay, well here, we know that actually, there is, if we have a sound wave like this,
yes.
well, our ears will actually correspond to the result like the STFT graph. But however, the time, like, mainly the time here is not changing. The length here is not changing. Okay. Yes.
So, what is your wavelength in your experiment you measure? Your
wavelength?
Sound wavelength. Can you show your?
Well, I believe that it's not wavelength, but the period of time.
Period. Okay.
Well, yeah, nearly 0.0022 seconds.
Okay. The preparation of the opponent. us such a great.
Okay, start the opponent takes the floor.
Okay, thank you. So thanks to the reporter for giving us such a great presentation. And I'm the opponent from Hint and Exit RBO2. So first, let's first take a quick review of the problem statement. And you can see that the problem statement stated that two vehicle or similar are brought into context and have produced a chirping sound. And the problem wants us to discuss about the nature of the sound, which I think will be a very important factor that we'll discuss in the later discussion. And the main point of the reporter is he defined that the chirping sound of what the problem statement wants us to do is the increasing or decreasing of the frequency. So if difference here between the one contact collision and multi-collision will form and analyze it, because they found out actually it is very two different kind of sound, and have discussed about what's the difference of the sound in this presentation. And he has talked about the differences between forest transform and short-time forest transform, which have different results and have different meaning in this experiment. And the simulation of the tripping sound are the sound with time gap and the sound without. And he used the simulation to clearly tell us that the increasing frequency we hear is mainly caused by our ears hear, but actually the frequency he mean in his experiment, the wave period didn't change throughout the time. So in the collision of the time gap, which have discussed detailed in his experiment. So also in his experiment, he have changed the parameters of magnetic field and mass of the ball, which will influence the time gap due to the multi-collision. And I wish to skip into my discussion. Thank you.
To the discussion between the reporter and the opponent.
So since I think there are some places you need to clarify. Can you turn to a page where you show your short time force transform?
Which page, please?
Where you can show the increasing frequency.
Increasing frequency. Number page 15, please.
So first, in your experiment, you discuss about the equivalent frequency of the time gap, and you use one line to fit your experiment. But do you notice in your graph there are actually two increasing frequency, and what does it actually mean?
Okay, so first we have to go back to what exactly the short-time Fourier transform is doing. Well, the short-time Fourier transform is simply windowing this thing. So he is adding windows, these graphs. So it will observe, like this, it will observe a frequency like the response frequency like this. But if it includes, like when the time gap starts to increase, with same window length, it will include this part.
Yes.
So it will experience a wave here, a wave like this. So, because Fourier transform is doing the sinusoidal adding. So if it goes on to increase, it will also have the double time of the frequency, the
overtone, something similar to the overtone. Do you mean by the?
Yeah. I'm not actually sure about the English word, but well, it will also correspond to its integer times of its frequency.
And have you noticed that since that there are some frequency higher and some frequency lower on your upper part, which you said that it actually is the nature of the sound. So do you think this is also the cause of the overtone?
Well, first of all, I have to explain that maybe you would think that this graph is kind of blurred. Like this graph is kind of not so clear. Well, we have to first explain the original limitations of short-time Fourier transform.
Oh, by the way, in your experiment,
yes,
you record the background noise when you are analyzing your experiment.
Background noise?
Yes, have you first recorded your background noise before you analyze the sound?
We have subtracted it out.
So how do you subtract it out? You first record the background noise,
yes,
and then
we have the time sound pressure of the sound pressure of the background noise, and then we have the sound pressure of the recording.
So So then, how do you transform the decrease the effect of the factor noise? How to minimize the effect when you analyze? Do you subtract the waveform, or what kind of process do you use?
I simply subtract the waveform.
Oh, okay.
Yes.
And by the way, do you notice that I have a question about the graph about the sound pressure. I don't know, is there a unit in your experiment?
Well, for the sound pressure part, because first of all, it's the experiment that we use. The microphone is simply measuring the sound pressure in an arbitrary unit. Like, we can't compare different sound pressure graph in different graphs. It is like a normalized value in each recording process.
Oh.
Yes, so we can't compare, but we can compare the one in the same recording process in the same graph.
Okay. And since you said that the time gap actually is equivalent to frequency, the inverse of time gap is equivalent to frequency. I think actually you can say that it actually is the frequency, because the frequency is the definition we can define as the inverse of the period. So, and in your experiment, you said that each time gap has for example, because a period means that the time through wave affect to have a similar condition. So if you have a wave like this, and you have a time gap in a wave like this, actually, I think we can call this as a period. So actually, I think that your frequency, your time gap actually means that it also has a frequency.
Well, I have to clarify what am I meaning here. What I'm meaning is that since the very origin of the sounds come from the vibrating of the ball. So since it's the same ball, we believe that the vibrating frequency is not changing. So the time period you're mentioning here, this one is not changing. However, there is also a frequency corresponding to the raising and decreasing time gap, which contribute to the frequency you mentioned. So, of course, I agree with you.
Actually, I think that in your experiment, I think this should be considered as a pulse, not a wave. Is a periodical wave, and I think you should consider the whole thing as a wave. And the pulse, the time of the pulse is not changing at all, because due to the vibration of the steel.
Yes, I agree with your point of view.
Okay, and since that in your experiment, you have done simulation of one wave and two waves.
Yes.
Show the sound again.
On page 36.
You said you simulated the time decrease is because the collision is in elastic collision. Am I correct?
Yeah, it's related.
So what will happen, or what will happen to the time gap if it is a total inelastic collision or elastic collision?
Total and elastic.
Or elastic.
Well, okay. First of all, the total and elastic one, it won't. All energy is dissipated, so there won't be any. The energy is transformed into the deformation of the steel ball, so there won't be any next collision. And for the total elastic one, well, we believe that the time gap won't be decreasing; it will be lines.
So it will be like your first simulation in your experiment.
Similar.
Okay, I got it. So since in your formula you have discussed about, can you show your formula?
The formula of what exactly?
The elastic collision.
Okay. Page 28, please.
So since we still, have you investigated the initial velocity here in your experiment?
No, not exactly. I'm sorry.
So can you predict about what will happen?
Okay. Well, because now we have only validated the relationship between M and the magnetic field, I'm not actually sure whether the prediction is correct, but if this theory is close to the real conditions, then of course the time gap will be in a positive relationship to the initial velocity.
And since your wave look like your pulse
Yes.
look like kind of like think that it is kind of similar to the wave package.
Okay, well,
Do you think it's there, like, when we analyze as, what do you think is the difference between your pulse and the wave package? Like, when we put two graphs together.
yeah, okay. Well, here we have, I believe that the wave package you're mentioning is like adding different hertz of sound together.
Yes, but that's the decreasing and the increasing amplitude of the wave package is because the lower frequency is canceling out the amplitude of the
Yes.
your
Yes.
higher frequency.
So, yeah.
But in your experiment, there's now a lower frequency to cancel out the pulse. So what do you think is the same effect?
Well, we believe that the reason that you said the amplitude is canceling out or adding up is because of the different frequency corresponding. And in our experiment, in the chirping sound here, we believe that the canceling or adding up, mainly adding up, is because of the collision, the single collision. The collision will, like, when it's vibrating, and the collision will add up to the vibration and result in
here
sound
is
pressure.
a single pulse. You said in your experiment, your graph, when you only contact once,
Yes.
you can see a sound wave.
Yes.
And by this, I mean it is only a sound. If you see a sound wave, it's kind of like a wave package, which the amplitude in the front is much bigger than the amplitude in the, it's much smaller than the amplitude from the middle. So, what do you think would cause the...
I'll show my graph first. Page 21.
Yes.
I mean, what's
You
exactly
can
is.
see when you use multiplication.
Yeah, yes.
You can see that there's an increasing and decreasing of the amplitude in your pulse.
Okay. Well, maybe we can go back to explain just focus on single collision, since you are mentioning a single collision, right? So for a single collision, there will be like two balls when they bring into contact. Well, we simply assume that two balls are both vibrating.
Yes.
And if we collect the data from some point over here, then there will be a difference of path.
Yes.
So maybe we will experience a different, like the add up and not adding up, the subtraction of
Don't you
subtraction.
think it is caused by the vibration of the ball? Like, first of all, after collision, the ball vibration, and after that, it kind of didn't stop vibrating and wait for the next collision.
Yeah, maybe a reason for the decreasing of him.
And since you have the time gap
Yes.
from each collision,
Yes.
can you calculate the coefficient of restitution in your experiment?
It may be possible, but we didn't do it. And because we are using the magnet, and the magnetic force, the magnetic field is not equivalent to the magnetic force. Just simply.
You can check before each time gap. Well, is the coefficient of restitution, is it constant? So if you have to do this part, you can more convince me that it is a elastic collision, and which the time gap will affect on the constant force.
Sure.
And I think I have a good understanding of the problem, and thanks for your discussion.
Thank you.
Okay, thank you. So the opponent summarized the question.
So, thanks for the reporter for giving us such a great presentation. We have clarified the chirping sound is the increased frequency, and it has shown in this short time Fourier transform graph. And we have clarified why there are two increasing frequency in the experiment in this graph. But clarifying the unit of the sound pressure is only a comparison value of each pulse or each wave's amplitude. So, and discuss about the elastic collision and what will happen if the elastic collision or total elastic collision happens, which the reporter had a great answer, and I think I agree with him too. So, and discuss about the wave package, how the wave package is formed, and how it is composed to a single pulse in this experiment. So, and discuss about the calculating of time gap. I think there's weaknesses of the reporter is that he should check and using the time gap to check if the coefficient of restitution is constant to match match his theory. Since he didn't do that, I think he could improve his experiment by calculating and show us the math process. Thank you for your listening.
Thank you. The reviewer questioned the reporter and opponent. The end question.
So I'm the reviewer today from the Yellow Dot, and now I have some quick questions for the reporter.
Yes.
So since you have mentioned a lot about the time gaps in your report, and I would like to ask you, so let's imagine if the time gap is bigger, like for example 10 seconds or 5 seconds, and what will happen?
When the time gap is bigger, simply is like when we collide two steel balls, like 10 seconds after 10 seconds. And because this is actually related to the response time of our ears, and which corresponds to the the window length of the short time Fourier transform. So if the window length is not so big, relative to the time gap, then there won't be the increasing frequency we observe.
Okay, so can you give us the accurate reaction time that you mentioned?
Reaction time, well, I believe it's nearly 0.01 seconds.
Okay, thank you. And for the reporter and the opponent, can you define the nature of the sound? And first, for the reporter.
Okay, the natural results of sound, we believe, increase, including some important elements, including the frequency, the amplitude, and also the waveform of the sound. And in our experiment, because it's the chirping one, so we mainly discuss about the frequency one.
And I think it is about the time gap in the pulse in the experiment of the reporter. Because since the graph have two parts, which is one is the sound wave, and which is the time gap, I think it is dependent on both two factors, which will affect the nature of the sound. Thank you.
Okay, so again, for the reporter, can you show us the graph which the voltage one?
The voltage one,
Yes.
page 20, please. 20. Yes.
Okay. So as you can see,
Yes.
okay, so the line beneath the graph and the
Okay. So it's
Thank you.
so preparation of the reviewer. the reviewer takes the floor.
And okay, so I'm the reviewer from the team, yeah, the yellow ducklings, and today I'm going to review problem number 4, the bow sound. And so let's take a look at the problem statement again. And the problem statement says that when two hard balls frequently contact with each other, unusual chirping sound may produce. And the problem statement wants us to investigate and explain the nature of the sound. Okay, so first we will take a quick review at the reporter's report. So for the assumption that the reporters have made, the reporters assume that the magnetic force is constant when it is in the small region. And another assumption that the reporter had made is that the impact of the magnet or the steel ball is an inelastic collision with a coefficient of distribution. Okay, so and then to the analysis part, the reporter has compared about the Fourier transform and the short-time Fourier transform, and in his experiment, the reporter has used the short-time Fourier transform to analyze his data. And for the parameters that the reporters have done, he changes the different mass of the ball, and he changes the magnetic field of the magnet, which is the force applied to the steel ball. Okay, so, and for the reporter's experimental setup, he used a microphone to collect the data of the sound. And as the result of the report, when the two steel balls are brought together by hand, it will cause a chirping sound. But when the two steel balls are collided by a Newton cradle, we'll just hear a single collision. And the sound that is simulated is similar to the chirping sound. Okay, so here we come to the conclusion part. The result of the chirping sound is caused by the increasing of the frequency, and the time gap will influence the frequency as well. Okay, so first and then we'll come to the discussion between the opponents and the reporter. And the opponents asked about the size of the pole, and which the reporter said there will be no influence. And then the opponent asked about the time period, and the reporter said that it will be 0.002 seconds. And also the opponent asked about the short-time Fourier transform, and the reporter said that the short-time Fourier transform is actually adding windows onto the waves. And then the opponent asked about some parts of the pictures in the short-time Fourier transform, and the reporter also explained about it. And the opponent has asked about the background noise, and which the reporter has also solved this problem. And then okay, so we'll come to the advantages and the suggestions to the reporter. And the advantages of the reporter, he had expressed in the related series by the short-time Fourier transform, and he details the explanations about the continuous collision. And also he answered the statement. Okay, so and the suggestions for the reporter, we think that
Okay, the next stage is concluding remarks of the reporter.
Okay, thank you for the opponent and viewer. Here will be my concluding remarks. Okay, so thanks to the opponent for the advices on the experimental method that we could validate our theory more clearly by actually calculating the coefficient of restitution here. And thanks to our reviewer for mentioning the Windows response time. The relations of the response time of our ears is actually just like the short-time Fourier transform, the window length of the short-time Fourier transform. So when the window length is actually including the time gap, which corresponds to two collisions, it will start to include the time gap, the collision frequency into the results, so which will affect our hearing, affect the frequency of the SDFD graph. So the STFT graph has proved the increasing frequency of the chirping sound we record. And while the potential graph of with the sound pressure graph has validated the mechanism of multi-collision. So overall, we believe that we have enjoyed such a visit fight with the opponent and reviewer, and thank you.
Now, the questions from the jury. Professor Lee.
Okay, Professor Wu and I are discussing what's the real mechanism responsible for this chirping sound. We have different theory. Now, in order to verify which one is correct, okay. I ask you to play the sound of the Newton cradle and the collision with magnetic force again.
Okay, page 2, please.
What's the Newton cradle? Okay, then play the chirping sound. Okay, so you see, the chirping sound is a high frequency, right?
Yes.
Obviously, it's high frequency. Okay, now, for the Newton cradle, what we hear should be the natural frequency. One vibration of the wall is lower. But from your data, it shows that the collision frequency is much lower than the natural frequency. But what we hear, the chirping sound is high frequency, right? So, something wrong here.
By the way, do we have the sample size? The two recordings, are the balls of the same size?
These two
Yeah.
recordings, I'm not sure.
Visible from the picture, it seems that the balls in the Newton cradle system is bigger.
I'm sorry, this is just an observation. We were just demonstrating a phenomenon. We were just discussing it with this two sound. So I'm not actually sure if these two sounds are the same size. I'm sorry. Yes, because we were first just demonstrating a phenomenon.
Size cannot be very different, right?
Yeah.
It cannot be twice or 3 or 10 times.
Yeah. So,
I think I this because if you are first colliding, we know that Newton's cradle is like the first.
Short answer, please. Yeah.
The nature of sound comes from balls vibration, and when you are constantly colliding, maybe the distance can be shorter than maybe the time that can move the distance in light would be actually shorter than the vibration frequency of the ball. So I think that could be why we will have different frequencies.
His data showing that the collision frequency is much lower because in DMT data, the red curve is a low frequency than the blue curve. Blue curve is much faster.
At the end of the collision, it will be higher. That's what
You know, I think chirping are always high. Okay, well, what's the opinion for the review?
I think I just agree with the authorities.
Okay, so probably we move to the other jury. Okay. Professor Ye, for the reporter, what is your delta T, delta F in the analysis?
delta T? Well, we set the window length of 500 window length corresponding to the, we believe it's like around 0.00. I think it's around this magnitude. I'm not actually sure what it's about because we set the parameters.
For your responsible time? Responsive time?
Well, it's slightly smaller. Yeah, in an order of 10.
Okay, Professor Du.
I think it's important to ask a question. That is, if you look at the long time record. So, in your Newton's cradle, if you look at long time record, so you will have the same effect 5 minutes. Then the musical cradle, it go up and then down, up and down, up and down. So it will be similar to the multiple collision that you see when you use your hand. So, do you think they have the same nature?
The multi-collision is happening in both phenomena. However, we believe that the time gap has to be smaller, has to be so small enough to go into the region of the response time or the window of length of the short time Fourier transform for us to get such a increasing frequency.
The short time Fourier transform is a technique.
Yes.
So I'm talking about the sound itself.
The sound itself, well, because we can feel the difference when the time gap is bigger than the response time. So we will hear two collisions like two times of the single collision of the integrator. That will be what we hear. And for the one when the collision is faster, the time gap is smaller, then we will hear a chirping sound. That's what we believe.
Professor Wu?
From your frequency, could you please show us what's the natural frequency of the steel balls?
The nature of frequency?
Yeah.
Well, we believe it's around.
Yeah, because opponent chart, you mentioned a couple of times that there's a natural frequency.
Yes.
The ball is still on state. So can you just one of your slides to tell us what's the natural frequency?
We have calculated that this time is around 0.0022 seconds. So the inverse of it is around 4,500 hertz.
And how does this 4,000 compare with your chirping frequency?
It is
Can you show us some?
the one of the short time Fourier transform, or which one? I'm sorry.
Whichever the chirping frequency.
Okay.
Or give us a number roughly.
The chirping frequency is around 600 to 1,000 hertz.
Right. So it's like almost 2 order magnitude different.
Like two.
One order.
Yeah. 2 times. Well, what we believe is that because we hear these two sounds together, so we can actually distinguish.
Right. So you clarify that natural frequency is like 6,000 and the chirping frequency is like 400 something, right? Roughly.
4,600.
Okay.
Yes.
So this is a question for all three teams, and I want to get the answer in the reverse order from the reviewer, the opponent, and the reporter. This is related to the earlier question, and very important. What do you think is the frequency that we actually hear? Is that the natural frequency, or that's the collision frequency? If apparently there's a mix, and I want to hear your opinions about which one is actually dominant. Apparently, the reporter has shown theory already, and he clarified that, and I want to hear your opinions. Right, that's why I take a reverse order.
Okay, so I think the chirping sound will form this because of the increasing of the collision frequency and the nature of the natural frequency of the sound will change.
For the opponent, we have to make a short answer. I think it is something to do with our response time. Because we know that from high school physics, echo, we need to hear echo, we need a distance reflection must be higher than 70 feet. So it's bigger. So that means that if it is too close, we'll put 2 down as 1. So if the time gap is too close, we'll hear it at 1 sound. So we'll calculate, our ear will hear the frequency of the time gap. But if the time gap is more than our response time, then we'll hear 2 sounds. It's similar to the echo. It needs to travel more than 70 meters for us to hear 2 sounds, but not only 1.
In this case, do you think that's close enough? I want the answer.
You said the time gap is close enough?
Yeah, the question was actually very simple. Which frequency do you think we are hearing mainly?
Of the time gap.
Of what?
Of the
Collisions.
Not yes.
Earlier on, you said that you think the time X is smaller than.
I said at the end of the collision where the high frequency will, I think that's why we will hear more higher. But in the front, like the reporter have shown that the time gap is very big.
Can I give a quick clarification that? Because when the time gap continues to decrease, and we will maybe be misled by our brain that it's actually the same sound. So we will hear both the natural frequency and the collision frequency, and it will affect each other.
Professor.
So you have time gap model to explain the chirping, right?
Yes.
So you agree time gap model?
Yes.
You agree the reviewer? And this time gap, to support the time gap model, I think you use the so-called short time Fourier transform runs to analyze this time gap. So does it imply that our brain is also doing a short time Fourier transform to process the sound signal? Does it imply? Can you first?
Well,
Yes or no? Yes or no?
yes. Well, I thought I learned
You say yes.
Yeah, I believe.
Yes. You say
Yes.
You say yes. But in the beginning, you also said that our brain is doing Fourier transform. So how do we solve this?
Yeah, okay. I believe it's like this. It's like we're doing Fourier transform under a certain window of time. Like when I hear others speaking, I will do a Fourier transform every 0.01 second. So for at least 0.01 second, I will collect the data to tell us what exactly am I hearing. So that is why I say that it kind of corresponds to the mechanism of short-time Fourier transform.
And I agree with the time response time is equal to the window frame, which the reporter has said in the short time Fourier transform. And because our here have different kind of they have learned to correspond with each kind of frequency, and that's why we can have our ears can do similar things to the Fourier to have the effect of the short time Fourier transform.
If you use a piano or other music instrument to introduce a chirping sound, can you or how do you do that from the reviewer? Use a piano to generate a chirping sound. How do you do that, or can you do that? How about Poland?
If we use a single note as the initial frequency, like the steel ball, if we can hit the beat faster, shorter than our response time, then we can see there's a frequency difference in our hearing.
How fast would it be?
How fast? We believe it will be faster, like a second for more than at least more than 20 times. We believe more than 100 times will be ideal for hearing such a chirping sound with a single note.
More questions? Okay, the jury make the grade. Okay, for the score for the reporter, 8, 9, 8, 8, 8, 8, 9, 9, 7, 9, 7.
Thank you.
The score for the opponent, 7, 8,
The score for the reviewer, 6, 6, 6, 5, 6, 5, 4, 5, 6, 4, 6. Okay. So for the opponent and then for the reviewer, there's a lowest grade. Will the jury like to explain your grading? Okay. You want to make some comment, Professor? Do for the opponent or reviewer?
I think the opponent is not bad. It's just because I'm kind of ready to go. But one point I have to say that is the question for wavelength, I think, is kind of irrelevant. Okay. So, other than that is
Okay, thank you. Anyone? Professor Wu?
Just a general comment. I think it's not easy for a reporter to get a full on because there's always something that's insufficient in discussing the problems. That's why I couldn't give higher than that. But actually, apparently he has done a good job. And for other teams, actually for the opponent, I think he should focus more on the context of the reporter's presentation. And if a reporter didn't give a thorough presentation, then the opponent can actually try to help to enhance the content rather than just to criticize without giving a specific answer or piece of thought. And for the reviewer, he should focus even more on the physics rather than the details of the presentation, for example. So this is just a general suggestion that, especially for the reviewer, you should focus more on the physics of the discussions rather than the detailed diagram, page number, that kind of thing. Yeah.
Okay, thank you. So we close the second round and take the 10 minutes break. Thank you.